All right, welcome to lesson 7.6 on trigonometric equations. I'm recording this in a different fashion than I usually would, but I had some free time at school, so we thought we would try it, okay? So the essential question is, how do I use trig properties to solve equations? And so we've been working with these different trig equations, trying these little tricks quite a bit, and so this is our last section on that, and our last section in the year, I believe. So number one here, it says, solve a trigonometric equation using a linear method. So it says, solve the equation 3 tangent of theta minus radical 3 is equal to 0. And so basically what we're going to do is we're going to use the same trick as we would if we were to solve something like this. Okay, we're going to use that same trick. And so we're going to have our solution first off be over the interval from 0 to 360, pretty standard. So what we're going to do is we're going to first add root 3. And then we're going to divide by 3, right? You just get the tangent of theta alone. So we have this. So this is something that we've solved in the last couple of days. And so we're looking for the values of theta where tangent of theta is root 3 over 3. So now we know tangent is positive, and so we only have two options. We have quadrant 1 or quadrant 3. Those are the two where tangent is positive. And remember, tangent is sine over cosine. So if we actually look at root 3 over 2, if you recall this on the side here, it's hard to see, it's weird for me. Root 3 over 2 over 1/2. This turns into just root 3. So that's no good, right? Because it's root 3 over 2 times 2 over 1. But if we look at 1 over 2 over root 3 over 2, which is a little bit more common, this turns into 1 over root 3, which when you rationalize it turns into root 3 over 3. So we're looking for this behavior of sine over cosine where it's 1/2 over root 3 over 2. So that means that what we have for answers in quadrant 1, where we have the sine being 1/2, is pi over 6. That's in quadrant 1, because then we have 1/2 over root 3 over 2, like we just talked about. And then in quadrant 4, where the sine is negative 1/2, we're going to have 7 pi over 6. Those are the two solutions that we would have to start with. Now, you could put that in degrees if you want to. It would be 30 and 210. That would be fine as well. But that's it. Okay? Now, if we remember the period for tangent, remember tangent goes from negative pi over 2 pi over 2, so the period is pi. That means that what we really have over here for all solutions, this isn't just for the interval 0 to 360, but it's for all solutions. Remember, these trig functions go on forever. Okay, they're periodic. And so all we have to do is take our values, our pi over 6 and 7 pi over 6. And I guess if it wants us to have 0 to 360 degrees, we should probably put it in degrees, right? So 30 degrees, 210 degrees. You do that by looking at the unit circle or by just converting, right? Take it times 180 over pi. Okay, so here's the two answers. For all solutions, if we know that the period of tangent is going to be pi, all we have to do, or 180 degrees, if you will, all we have to do is continue adding 180 degrees, and that'll give us the same value. So what we're going to do is we're going to create, well, I guess we're going to have a solution set down here of 30 and 210. That's how they're going to have us write this, a solution set. So our solution set for all solutions would be 30 plus 180 times some number n, right? You can do it once, you can do it twice, you can do it 3 times, you can do it as much as you want, okay? Where n is any integer. So do 30 plus 180n, and if you imagine, if we add 180 to 30, we get 210, so we don't even need to add another one, right? We don't need to do 210 plus 180n, because this is the same thing. So right here is just our solution. It's good practice to write a little semicolon. N is any integer, just to describe what n actually is, so we're not just blindly writing variables, right? That will give us all the values for this equation. Okay, so essentially you're going to get the tangent portion alone, use what we did before to figure out what theta would actually be, and then you have to think about a little bit, what does this mean for our equation? Okay, so that's one method. It would just use the same trick you'd use to solve this, and we're good to go. Okay, the next one we have it's really hard to see this. We have the zero factor property. This is something that you learned in geometry, okay? So the idea, or in algebra, the idea here, trying to line this up, is that if we had two things that equal zero, A times B is equal to zero, that means that either A was zero or B is zero. Because if you try to think of the pairs of numbers that multiply to zero, you think of things like 2 times 0, 3 times 0, and so on. And no matter what pair you think of, there will always be a zero. And so this is the property that we're going to use to solve this one. Now, it's tempting, right? Because it's really tempting to first divide by cosine on both sides, so the cosines cancel and be good. The issue is that if you divide by cosine, you have to first think about what would happen if cosine was zero, because you'd be dividing by zero. And so usually you want to try to avoid dividing by any variable expressions just for that circumstance. You kind of work around it, but that's usually the best bet. So what we're going to do instead is we're going to get it equal to 0 first. So we're going to do the cosine of theta, cotangent of theta, minus the cosine of theta equals 0. That's just subtracting that cosine on both sides, nothing crazy there. And then we're going to use that GCF factoring method from your past. Go ahead and factor out the cosine of theta here. We left with cotangent of theta minus 1 is equal to 0. Okay, and so now we have these two things. We have two things that are multiplied to be 0. And so now we set them both equal to 0. So either the cosine of theta is 0 or the cotangent of theta minus 1 is 0. Now we have two different equations to solve. Okay? And so for the left side here, the cosine of theta is 0 when theta is between 0 and 360. Remember, cosine is that first coordinate. So we're going to have pi over 2. And what else? Cosine is 0. It'd be 3 pi over 2. That would be our two solutions for cosine of theta equals 0. Now, cotangent of theta is equal to negative 1. So it's a little bit different. That means that cotangent of theta is equal to 1. Now, cotangent of theta being 1 is the same thing as tangent of theta being 1, right? So if you think about it, we're in quadrant 1 and quadrant 3. Those are the two where the signs of the signs match, right? Either they're both positive or they're both negative. And if it's 1, that means they both have to be the root 2 over 2 portion. So that means that theta here is going to be pi over 4, or the pi over 4 equivalent in quadrant 3, which is 5 pi over 4. Okay, so it does have it degrees up here, so it's probably in best practice to put it in degrees. So we'll have our solution set here. Pi over 2 is 90 degrees. Pi over 4, I should have done that one first, huh? Do I want pi over 4? I totally want pi over 4. Pi over 4 is 45 degrees. I should put that first. Oh, a little messy there. 45 degrees, 90 degrees. 5 pi over 4 would be what? 225 degrees. So we want 225 degrees and 270 degrees would be our value there. Okay. So nothing too terribly frustrating there. I have to make sure I did everything correctly. Cosine of theta is 0. That one is, of course, true. Cotangent of theta minus 1 is equal to 0. I solved this properly. Yeah, we should be good here. Okay. So nothing too scary on this one. Again, this property right here is what we really wanted to focus on. There's going to be a couple different methods here, and that's what we actually want to do. Okay. All right, go on to the next one. Okay, solving a trig function or trig equation. Now this is going to be factoring. Now it was zero factor property again, but what we're actually trying to do here is factor a little bit, if you will. Okay, and so what we're going to do is we're going to try our best to turn this into a quadratic equation. Okay, now that's a little bit scary for a lot of you because it's going to involve factoring, but we're going to be just fine here. So the idea, and this is something I learned a long time ago, the idea is we see this as a form of this, right? The book's saying you should be able to see this equation down here in this form. Now, that may not be obvious, and so what I learned in school was if we let some variable u, this is let, it looks like 6t, it says let u equal sine of x, okay? Just we're going to use that as a placeholder. We're going to rewrite our equation as 3u squared, right, 3 sine squared, minus u, that's sine, minus 2 is equal to 0. Now, that's a bit easier to see that it's a quadratic equation for me. So let's go ahead and work with that. We'll factor that, bring it back, right? We're going to bring it back to the sine equation and solve from there. Okay, so maybe you don't need to do that. Maybe you see it. But now in our school, we do a lot of TLC factoring, right? This is TLC is greater than 1. So I'll teach it that way here. We'll talk about it. Hopefully you remember how to do this. But the idea was that we had a little x. The two numbers multiplied are -6, and they're added up as -1. So what we're looking for is -3 and 2, because -3 times 2 is -6, -3 plus 2 is -1. They may have never seen this, but this is how we factor. And so now you can rewrite that middle term as the -3u plus 2u, right? And now this is still -u, nothing has changed. And now we factor by grouping, right? So out of the first two, you take out a 3u, you're left with u minus 1. Out of the next two, you take out a 2, left with u minus 1. Out of both of those, you take out a u minus 1, and you're left with 3u plus 2. Okay? And now, so we factored at this point, which you could maybe have done without showing any of this work. This might not be necessary for you. And now we plug our u back in. So what we have here is we have the sine of x minus 1, parentheses, 3 sine of x plus 2 is equal to 0. And so all that work right there is just to factor it, okay? And so now we want to use that 0 factor property where the two things multiplied to be 0 means that each one is 0. And we're going to go ahead and do that. So that means that sine of x minus 1 is equal to 0, or 3 sine of x plus 2 is equal to 0. And we're going to solve each one of those separately. So we have sine of x equals 1, or sine of x equals -2 over 3. Okay? So this one's going to take a little bit of approximation. I bet I don't have a calculator in me. Hold on. I don't. I totally don't. If you're my student, you know I don't like to have a calculator around me. I like to make my students do it, okay? So the sine of x equaling 1, that one's easy to find, right? Sine is 1 at, oh, I bet that's where, oh, no, that's fine. So sine of x is 1 at pi over 2. Of course, we're in radians again because this problem says 0 to 2 pi. At pi over 2 and 3 pi over 2. We might have to go back to last problem. I might have had sine in my head last problem. I'm just having a little bit of memories here. So that one's where that's true, in 0 to 2 pi, okay? Now, if we want sine of x equals -2/3, -2/3 is certainly not on the unit circle, right? So our best bet here is to approximate this. So we're just going to do what you learned. We're going to do the inverse sine of -2/3, okay? So on your calculator, mine's old school. I need to be in radian mode. Let me grab a better calculator that'll actually show up under the camera. Hold on. Okay, so here's our school's calculator. We need to be in radian mode to do this. So right now I'm in degree mode. So I push mode, go down to radian, push enter, go back to the screen. So now we're in radian mode as it says. It's kind of still hard to see. Okay, so what we're going to do here is we're going to go ahead and type this in. So we have sine inverse of -2 over 3, right? That's what we have. So I wind up with this answer right here, -0.7297, so on, okay? We'll just do 4 decimals, okay? So that's what it says. Now here's the issue. We want solutions in 0 to 2 pi, okay? And that is not between 0 and 2 pi. So what we're going to do is we're going to add 2 pi, which is the period for sine, right? We're going to add 2 pi to this. So we're in decimal, so I'm going to add 2 pi. So -0.7297 plus 2, where's pi? It's not a button I use super often. There it is, 2 pi. So we have 5.553, let's go with 5 there. 5.5535 as our solution there, okay? So there is our one option right here, okay? And that should be good enough. So there's our three answers. We have solution set pi over 2, 3 pi over 2, and 5.5535 as our solutions. Okay, it's just three of them. Nothing too terribly crazy there, okay? I think we can get one more in this video, okay? Now this one's the quadratic formula version. Again, all of these are just equating to solving these different quadratic methods that you learned back in algebra, okay? So here we have cosine of x times cosine of x plus 2 is equal to 1. So what we end up with here is if we actually work through this, right, we distribute the cosine, and we get it on the left side. So we have cosine squared x plus 2 cosine x minus 1 is equal to 0. Okay, you end up with something of the form, right, on the side here, u squared plus 2u minus 1 equals 0, okay? And so if you think about factoring that, you need two things that multiply to -1 but add up to 2, which is not something that you can actually factor, okay? And so we're going to use the quadratic formula. Now you probably learned a song to remember this, but we know it's x equals a negative b plus or minus the square root of b squared minus 4ac all over 2a. Now what we're going to do is instead of using x, we're going to use our variable as the cosine of x here. So we're going to say the cosine of x equals negative b. So again, this is talking about this form. There's your general form, right? So negative b, so negative 2 plus or minus the square root of b squared, so 2 squared, minus 4, a is 1, c is -1, all over 2a, so 2. Okay, so just that nice little equation. So we have cosine of x equals -2 plus or minus. Let's do the inside portion. So 4 minus a -4. So 4 plus 4 is root 8 all over 2. How nice can we make this? So we have negative 2 plus or minus. This is 2 root 2 all over 2. So we get, divide everything by 2, we get -1 plus or minus root 2. Those are our options, okay? And so let's go ahead and just give a decimal form, if you will, because it's going to be a little bit easier to work with if we just have it in decimals, because otherwise we're going to have some really nasty answers. Because what we want here is we want to take the inverse cosine. So this is either cosine of x is equal to, there's two options here. So we have -1, let's get the calculator back out here. -1 plus root, where's root? Root 2. That's the plus version. So 0.4142, I went too far. Right here, 4142. Or cosine of x is equal to, and so we'll do -1 minus. That's not minus, this is minus. Root 2. So we have -2.4142. Okay. So a couple of things. First off, we have to do the inverse cosine. So when we do this, we just take the inverse cosine of 0.4142. So 0.4142, just to be consistent with our work. So we get x equals 1.1437. And on this side, inverse cosine again. -2.4142. Oh, so this is the issue. This is not actually in our domain, right? So we need to actually add 2 pi to this. That'll give us the equivalent of this, right? Because we have to be in the actual domain. So cosine inverse of 3.8689 if it's possible. So second cosine 3.8689. So it does not work. So this one's not going to be an actual answer we can get. So what we get here is 1.1417 as our final answer, okay? Now, we want to be able to add any number here. And so what we need, how much of this can you see? I'm sorry, it's really weird because it's mirrored for me. Now we want all solutions, not just some solutions. I just underlined all solutions on top. Okay, so we need to add on all integer values of 2 pi. Okay, so 2 pi m. Okay, now had this worked, we would need to check to make sure that both solutions actually worked. And I'm a little bit confused why it didn't work. I mean, this is not going to be in the domain, so it's going to fail. But maybe I messed up here somewhere. But in general, there's going to be 2 solutions here, and we need to be able to check both of them to make sure they actually work for us. Okay. So that is going to be the main idea there. That should be good enough for this section. So we'll stop the video here. We'll make another one.